Do I have this on? Sounds that way. Great. Okay, it's great to be here talking with you today. It's always awesome to be back in Santa Cruz. And I'm going to be talking about dwarf galaxies. And I realized when I made this title, actually after I made this title, that this whole halos of dwarf galaxies is a little bit ambiguous. And I do care a lot about dark matter halos, but today I'm going to focus on gaseous ones, as well as everything that is within that as well. I'd like to highlight my collaborators here. In particular, Allison Brooks is going to be giving a talk tomorrow morning, which will deal with the same set of simulations. So hopefully this will just prime you for her talk. All right, so what can dwarf galaxies tell us about galaxy evolution? And hopefully you're convinced about the value of these since we've been listening to several talks about them. But just to overview, first of all, dwarf galaxies are highly varied, which means that there's a lot of physics which is going into them. A lot of different processes which happen to do with galaxy evolution, and this can manifest in a wide variety of ways. Because of their small potential wells, dwarf galaxies are especially susceptible to processes that can either prevent gas accretion, as we just heard, or that can spur gas removal. And this could be environmental, for instance, tripping, or this could be an internal process, for instance, outflows driven by stellar feedback. If you look at this plot over here, this is showing mass loading factor. So that's the rate of mass loss divided by the rate of star formation as a function of halo circular velocity. And you can see in the dwarf galaxy regime, these mass loading factors are really high. In other words, somewhere between 10 and 100 times more mass is being lost than star is being formed. So that's impressive. I should also point out what these data points are. The color data points are data from a suite of simulations, Christensen et al. 2016, measuring these at different redshifts. And the solid line is just a fit to that. But on here, I'm also showing results from the fire simulations. That's the Muratov et al. 2015, long dash lines here. And two analytic models, the momentum-driven winds, that's the dot dash line, and the energy-driven winds, which is the other dash line. And all of these models predict high rates of gas loss in dwarf galaxies, but they also all diverge from each other down here, which means that dwarf galaxies are a really important constraint on understanding gas loss from galaxies. Or to put it another way, we can't just constrain our models with the Milky Way. We need another data point to make a line. All right. So, with this in mind, the composition of dwarf galaxies, so in particular the baryons and the metals in the form of both stars, ISM and CGM, can inform and constrain galaxy formation models. And I'd like to study that. Good now? All right. So gas particle masses around 1,400 solar masses, softening lengths of 60 parsecs. These simulations were computed using Chonga. think I'm the first person to talk about Chonga today, so very briefly. This is an SPH code. It is developed using the same physics as gasoline, but it includes a dynamical load balancing scheme, which makes it have very efficient scaling up to 100,000 cores. I've included on here some of the physics which is within these simulations. I'll just highlight a few things. These simulations include metal line cooling and turbulent metal diffusion. Our star formation is based off of the local fraction of molecular hydrogen, corresponds to the observational connection between star formation and molecular hydrogen. However, if you're interested, please talk to me offline because I have an undergraduate student, now a graduate student at Northwestern, who's been looking at the effect of making the dust shielding the criteria for star formation. For stellar feedback, this is done using a blast wave supernova feedback model. These simulations also include supermassive black holes. So to give you an idea what one of these volumes looks like, I'm showing Captain Marvel up here. You can see the zoom-in region is following filaments, which contain a number of dwarf galaxies. There are 11 galaxies in this particular simulation. The most massive one is the one we're zooming in right here, and this is about 10 to the 10 in virial mass. You're seeing gas here and dark matter here. I'll let it zoom in one more time so you can see that we do have some structure to the gas. All right, so let's talk about what's in these things. So first thing to look at is the stellar mass-halo mass relation. There are a couple of things I want you to take away from this. One is that the colored points, which are our galaxies in these simulations, fit pretty well to the models. The other thing I want you to take away is that at any given halo mass, there's a wide variety of both stellar mass and luminosity. So this gets back at this idea that for dwarf galaxies, there can be many different evolutionary trajectories. These things are diverse. We can also look at or to highlight that a little bit farther, I'm showing the star formation histories up here. These are each of the different volumes. And the individual lines show the cumulative star formation history normalized by the total mass of stars formed within the halo by redshift 0. The colors correspond to the virial mass of the galaxy. And you'll see several different types of star formation histories. So there are those dwarf galaxies which continually form stars. These tend to be in the most massive halos. We also see galaxies which are quenched at around the time of reionization. These tend to be the least massive halos. Some more interesting cases, there are some halos which start off forming stars, pause, and then start forming stars again. Star formation, effectively they have a gappy star formation history. And I'll talk more about that later on. And finally, there are a few galaxies in which the star formation only happens very late. These are interesting. These are extremely metal deficient. They are also very low stellar mass. Let's see, they've got luminosities, V-band luminosities between 10 to the 5 and 10 to the 6, so incredibly faint. And we only see them in these field environments. There's a prediction, or these were first observed or found in simulations in Shin 2014, in which she found that star formation in these halos can be sparked in part through interaction. And we see a similar thing right here. We compare these star formation histories to observed star formation histories. We again see that observed star formation histories can be similarly continuous. They can also be quenched, and they can be gappy. There haven't been any galaxies observed that have no star formation at the beginning and eventually start up with some. So maybe that's odd. On the other hand, we wouldn't be able to detect these yet, even if they did exist, especially since they only seem to appear in our simulations in the field. So in addition to looking at the stars, we can look at the metals, showing the gas phase mass metallicity relationship here, the stellar one here. In general, these are good fits. You'll notice a couple of outliers at very low stellar mass. But aside from that, galaxies seem to have the appropriate amount of metals. To dig in a little bit deeper with the metallicities, we can look at the relationship between stellar age and stellar metallicity. What I'm showing here for our 4 most massive galaxies. Well, 4 example galaxies. These are, I believe, the most massive, close to the most massive ones. And their stellar masses are listed up here. And a couple points to take away. One is that there's almost no evolution in the metallicity after 2 gigayears. So the chemical enrichment reaches an equilibrium. These continue to form stars. You can see that because there are blue points up into the current time. But the metallicity doesn't rise, or rises only slightly. We do see some evidence for mergers in this. In particular, right here and right here, we can see material is coming in, and it has had, these stars formed within a less massive halo. They have lower metallicities. And at any given stellar age, there's a very small spread. And this is, in our simulations, due in a large part to the metal diffusion. Now, I'm not showing here the standard deviation of the metallicity distribution function. I'm happy to show those to you offline. They are, to the extent that we've been able to compare them, consistent with observations. All right, so I've talked a lot about what is inside these disks of these galaxies. We've seen some hints about how star formation is happening and about the metallicities, but let's talk about the stuff which is no longer in the disk. So to give you some framing here, here's what we know observationally. So observations of galaxies show that these galaxies do not retain much of their metals at all. This is true for dwarf spheroids. And the one dwarf irregular that's been observed, Leo P, about 95% of the produced metals are neither in the stars nor the ISM. So that means that the vast majority of these metals are getting expelled from the galaxy. If they aren't in the disk of the galaxy, you'd expect that they would be nearby, probably in the CGM. And there is observational evidence for metals within the CGM. If we look at Bordeloi 2014, this is looking at absorption quasar spectra. And they find that there is a mass of carbon in the CGM comparable, at least, to the mass within the ISM and more than the mass within the stars. So these metals are getting expelled out into the CGM. We also know that if we look at other ions than, say, carbon-4, there's evidence for oxygen-6, which is a high ionization state. So this material is out in the halos, and also it is kind of surprisingly hot. Okay, so this is interesting. We'd like to know if our simulations similarly show material out within the CGM and what state that is in. Before I get into that, I talked about the CGM as this reservoir of materials that was in the disk. Something very cool, though, is that the CGM also impacts the future of the galaxy. So if you remember early on, I mentioned these star formation or histories of dwarf galaxies which had gaps in them. This is work by Anna Wright, who is a graduate student at Rutgers, and she's looking at an earlier generation of these simulations, and she found 6 galaxies which show these gappy star formation histories. Here's an example of one here. This is star formation rate versus time, and you can see that there's a pause during which no stars are being formed. And what she found happening is shown up here. So this is the halo, or the galaxy in question. This is during the time when it is quenched and not forming stars. A nearby galaxy undergoes a large outflow event. This results in a plume of gas coming out and actually interacting with this halo of our target galaxy. It does so with reasonably low ram pressure, which means that rather than stripping the target galaxy, it actually encourages gas to be accreted onto the disk. And we can see that here. So this is the mass of gas within the halo as the dark line, and the mass within the disk as in the dot line. And you can see that while the mass in the halo is fairly constant, the mass in the disk changes abruptly, and the star formation happens once this disk mass increases. And we've been able to confirm just by particle tracking that the material that's going into star formation in this galaxy is originating in its own CGM. It's not being transferred by this nearby galaxy. Okay, so let's look at what's in the state of the gas in these galaxies. This is total baryons. Each bar is an individual galaxy. And I'm showing here the mass within a component divided by the cosmic baryon fraction times the viral mass of the galaxy. So in red, stars. In blue, temperatures less than 10 to the 4 Kelvin, so roughly ISM. We have cool CGM in purple, warm in green, and a little bit of hot CGM in yellow. And what's immediately apparent is that dwarf galaxies do not get their fair share of baryons. So most of these contain less than 50% of the baryons you would naively anticipate for a galaxy of this mass. This is consistent with what we know from observations, which is admittedly at the very upper end of what we detect. So this baryon census here is from the review paper by Tomlinson, 2017, originally in Molly Peebles' work, 2015, I believe. And these values roughly line up. So again, observationally, we see that these galaxies are baryon poor. What this doesn't tell us is whether these galaxies are baryon poor because they never accrete their baryons or because their baryons are lost. To figure that out, we can look at the metals. So that's what I'm showing here. We know that the metals originated within the disk of the galaxy. So now I'm normalizing by the yield times the total mass of stars formed. And notice now there's a log scale. Once again, we see that most galaxies do lose significant fraction of their metals, though these aren't as extreme as the baryons. Another way of saying that these galaxies are baryon poor in a large part because of lack of accretion. In fact, we can see that in the lowest mass galaxies, many of these galaxies retain near 100% of their metals. These are galaxies which are not powerful and do not have powerful enough star formation to expel all their metals. However, there are also low mass galaxies which do lose a lot. And this seems to be a factor of environment. So these same galaxies are also highly susceptible to any sort of stripping. All right, so the last thing I want to talk about is how we can look for where these are in the CGM. And when looking in the CGM, it's helpful to divide it up between different ions. So I'm doing that here with H1, oxygen 6, and carbon 4. You can see right away that the distribution is different. These are produced by cloud equilibrium models. You can see what sort of gas produces these by looking at the phase diagram. So here's the phase diagram colored by the amount of the ion at that point. And you'll notice that oxygen 6, carbon 4, produced by this, by the cool CGM or warm CGM material. I'll also highlight that we include an unphysical part of the phase diagram here. This is a function of the blast wave feedback model in which we have gas which is not yet allowed to cool. However, I will advertise that there is a new feedback model, superbubble, which I believe Ben Keller will probably talk about in his talk. And if not, I'm sure he'll talk about it with you in general, which fixes this issue. So we can take these and we can compare them with observations. And I'm looking at carbon 4 right here. So to orient you, each of these panels is one of the individual galaxies. I'm just looking at the 7 most massive ones, which are the ones that overlap with the observed samples. Bordelori et al. 2014, shown in either black or red. Birch et al. 2016, shown in either gray or pink. The colors correspond to the simulated galaxies which have similar stellar mass to the observed galaxies which have a similar stellar mass to the given simulated galaxy. And I realize that this is going to be very hard for anybody to see in the back. So here's the one for which there's the most data. So this is our most massive of the dwarf galaxies. And you can see that we are matching the observed relation to the extent that given that there seems to be a fair amount of scatter between galaxies. So you'll see these arrows are upper limits here, so we don't match these two, but then there's a lower limit up here, which we lie just underneath. So these things seem to be roughly consistent. It also seems to imply that there's a wide variety of CGM within galaxies of similar stellar masses. All right, so to conclude and what next? So I've shown you here a large sample of low mass and dwarf galaxies, which seem to follow Z of 0 trends. These have varied star formation histories with some evidence of environmental impact. And I've highlighted the fact that these galaxies are baryon poor, with most of the mass and metals contained within the CGM. And we can see that these galaxies have large amounts of carbon-4, which can be observed in the CGM. They tend to roughly match the observations. In future work, we'll do further comparisons with observations and look at the source and the future trajectory of material which is in the CGM. All right, thank you.
If I understood correctly, the neutral hydrogen is confined to a fairly small region in one plot that you showed. And I'm worried about that because downline analysis cover the entire sky at redshifts extremely above. That is, virtually every quasar at higher redshift has a downline analysis in there. That means that we have pretty high density, 3 times about 10 to the 20 atoms per square centimeter. Is that consistent with the simulations, or for some reason I cannot see the neutral hydrogen could be there but cannot see?
Right, so I was trying to pull up a slide which would show you the neutral hydrogen comparison, and I do not have that slide available right now. So talk with me, but to describe it, yes, there's this peak of neutral hydrogen here at the center. However, there is a large extent of neutral hydrogen farther out, and
What kind of column density?
these are basically consistent with observations. If anything, it seems that we have more neutral hydrogen farther out than all observations necessarily show.
So have you actually compared with the data on downline alpha systems?
We haven't done damped alignment alpha systems. I've compared with data from Burchard, and I'm waiting on data from Bordeloi. And the reason I didn't show it here is because it's not very constraining yet, but nothing would imply that we have too little H1.
I
Mm-hmm.
think that's the dominant component. If you have a centralized galaxy around a major massive galaxy, the dark halo will be strongly stripped in the whole galaxy with the strongly effect. And a little bit of wind is usually lost. So I think that would be the strongest dependent, that you can't get it into that dwarf galaxy into the dwarf galaxy or in the other way. There must be an enormous amount of effect. So I would suggest we should study that first. Separate the sample, satellite, and isolate it, and then you might.
So I should say that all of these galaxies are isolated for that exact reason. By isolated, meaning they are not a satellite. However, they still have an environment, and that even that small, relatively, even just looking at field isolated galaxies, we still see some impact there. Now, when we compare to satellite galaxies, which Allison will talk about more tomorrow, there are definite differences there. The reason we started with field galaxies is to get a baseline for that very reason. Yeah, we've specifically picked regions which do not have Milky Way galaxies in order to select for the underdense regions where you'd have a large sample of field dwarf galaxies. It's a matter of comparing apples to apples. So these dwarfs are a fair example
of